Welcome to Dr. C's Excellent Adventures. Today we're exploring Rattlesnake Crater, an ancient volcano on the eastern edge of the San Francisco Peaks volcanic field. The San Francisco Peaks volcanic field in northern Arizona includes over 600 volcanic vents that have erupted in the last 4.5 million years. These eruptions have produced a wide variety of volcanic landforms accessible by day trip from Flagstaff. Rattlesnake Crater in the southeast corner of the volcanic field was produced by steam explosions when rising magma hit groundwater.
Watch out for the shock, it's coming. Holy smoking Toledos.
A casual observer would be hard-pressed to identify Rattlesnake Crater as a volcano. Even on the geologic map, it just looks like a crescent-shaped ridge. It certainly doesn't rival Red Mountain or Mount Eldon as a hiking destination. Rattlesnake Crater is an example of a phreatomagmatic volcano called a maar. Maars are characterized by large craters relative to their overall diameter and relatively low ridges of ejecta containing abundant fragments of older rocks. Once you know what you're looking for, from the top of the ejecta ridge you can make out the outline of the original crater, which was filled in after the eruption ceased. One of the neat things about Rattlesnake Crater is that after the eruption ended, part of the ridge slumped back down into the crater, exposing a beautiful cross-section of the ejected material. In contrast to the strombolian eruptions that create cinder cones, phreatomagmatic eruptions produce layers of material that gradually slope up and out from the crater. The pyroclastic surges generated during maar eruptions are dilute enough that particles can bounce off of the ground or each other and may become well-rounded and coated with mud. The layering may exhibit reverse grading, cross-bedding, and channel forms, unlike the layering typical of cinder cones. These surges can also entrain large blocks of older material. In a 2012 paper, Valentine took advantage of the relatively simple geometry of the Colorado Plateau to evaluate below-ground explosive activity of the maar. Conveniently, the sedimentary formations below the surface at Rattlesnake Crater are the same ones that are exposed in the cliffs at Sedona. By carefully measuring and counting these pieces of sedimentary rock, which we call xenoliths, Valentine established that most of the material came from within the top 100 meters of the rocks below Rattlesnake Crater. This suggests that most of the explosive activity was fairly shallow with this volcano. The southern rim of Rattlesnake Crater is buried under a cinder cone called Rattlesnake Cone. Based on the similarity of juvenile basalt clasts, Valentine proposed that the crater and the cone were part of the same eruptive sequence. It's not hard to imagine rising magma interacting with groundwater and producing maar eruptions until the water was used up. Further eruptions would then switch to a strombolian style of magmatic eruption and build a cinder cone. In 2015, Marshall et al. Published a paper in which they combined gravity, magnetic, and ground-penetrating radar measurements to probe the plumbing system beneath Rattlesnake Crater. Shattered sedimentary rock should be both of a lower density and more weakly magnetized than volcanic rock. The fact that Marshall and company identified both gravity and magnetic highs beneath the crater suggests that the conduit was filled with lava which cooled beneath the crater floor. Their filtered magnetic map in particular really makes the volcanic vent obvious. So, given that Rattlesnake Crater is clearly a maar, what are the odds of an eruption like this occurring in the future in northern Arizona? Unfortunately, the age of Rattlesnake Crater is poorly constrained. It's normally magnetized, suggesting an age younger than 780,000 years, and in places is covered with ash from Sunset Crater, meaning it's older than 1,000 years. Within that time interval, the Earth's climate has varied dramatically. During periods of glacial advance, northern Arizona was much cooler and wetter than it is today, and presumably the water table was much closer to the ground surface. Did Rattlesnake erupt during one of these wet, cool intervals? Are those conditions required for an eruption like this? We just don't know. As is commonly the case in geology, Rattlesnake Crater is crying out for further study.